So chapter 1 is all focused on, well, I guess this is actually chapter 0, and this is my old PowerPoint, but it's all focused on all those concepts that we would have talked about in Algebra 2 and pre-calc. So we go back through and we just check on our ability to do all of those concepts. So this one is pretty easy. You're taking your calculator, you're plugging them in, and you're getting the number. As I stated, you want to make sure you always have a minimum of 3 decimals or 4. Those are kind of the rules in calc. So 3 or 4. At 3, you have 2 options. You can cut it off or you can round. They would accept both. So you can cut it off or round. And at 4, you just cut it off. So in 4, 5, and 6, you had to do the inverse property of those in a way. So if it was x for 1 is x cubed equal to 17, well, x cubed, to get rid of the cubed, you took your cube root. So this is really the equivalent of the cube root of 17. And that should make sense. All right, so today we're going to talk a lot about exponential growth, exponential decay. We're going to talk about applications of growth and decay. We're going to talk a little bit about half-life. Half-life comes back to us at the end of the year in integration. It's like in chapter 6. And then we also talk a little bit today about patterns and how we can use them in calculus and how we use our calculators to apply them. So the other day I didn't walk you through linear regression. Today we're actually going to walk through exponential regression. So in calculus, you'll find that you need to perform algebraic manipulations with negative exponents as well as fractional exponents. So it's important to know and understand the definition of a negative exponent and the definition of a fractional exponent. So a negative exponent is simply anything that is raised to the negative power. The a acts as the constant, the n is our variable. So a to the n to the negative 1 is equivalent to a over n. So anytime you have a negative exponent, that exponent can be rewritten in the denominator as a positive exponent. One of the mistakes I saw we make is that typically we take the a with us. Well, that a isn't raised to a negative power, so the a stays in the numerator. It does not follow the variable. Conversely, if you had b over x to the negative 2, that would be equal to bx squared. So if you have a negative exponent in the denominator, it comes to the numerator as a positive exponent. So again, negative powers do not make expressions negative. So sometimes students feel like, oh, n to the negative 1 means that that's a negative number. It does not. They simply create fractions. Typically, expressions in multiple choice answers are written with positive exponents. So that's why I so heavily stress being able to understand this. They're not typically going to give you a multiple choice answer with a negative exponent. Fractional exponents create roots. So at the beginning, the first example you did was 5 to the 2/3. So that is what we call a fractional exponent. That is a rational power. So that means it's not polynomial if this were a variable, but it also means that that's equivalent to a root. So the base number represents the number in front. So this is a cube root. And now there are 2 ways you can write this. You can write it with the 5 squared inside, or you can also treat it as the cube root of 5 squared.
So remember that multiplication is commutative. Therefore, an exponential root is also going to have that property. It doesn't matter the order we do it, as long as we do it, because technically 5 to the 2/3 could be equivalent to 5 to the 1/3 squared, because we have our power to a power rule. So if you have a power to a power, you multiply them together. So 1/3 times 2 is 2/3. Or it could have been 5 squared raised to the 1/3. So this is when math gets a little tricky, right? This is technically 5 different ways to write the exact same thing. There are 5 ways to write the exact same thing. So it's really important to know the equivalent statements between exponents and roots, as well as powers. When we multiply, it is super strange to students that when we multiply, we add our exponents. So if you had x to the n times x to the m, that does not become x to the n times n, but rather x to the n plus n. Division is subtraction. So x to the a over x to the b is equal to x to the a minus b. And when we raise powers to a power, we multiply. So that's the same as that 5/3 example. So that would be like x to the c, p would be x to the c times p, and I'm super running out of space. And it wrote that really big. So having attained that knowledge and reminders of all of those rules, let's apply them to some practice problems. So you have -8 x to the -2. We want to simplify this in a way that has no negative exponents in our problem, and all variables conform to a single variable if possible. So this would be -8 divided by x squared. Because again, the power is only on the variable, not on the coefficient. So the coefficient stays in the numerator, the variable drops to the denominator, as well as keeping the negative. That -2 in number 2 is going to distribute to both the coefficient and the variable. So this becomes -5 to the -2 times x cubed times -2. Because it is a power to a power for that variable, so they multiply. And then you have to simplify your numbers. So -5 to the -2 is really equal to, and I'm just running out of room, 1 over -5 squared. So with a positive exponent, it drops down. Well, now we know -5 times -5 is really just 25. So the power goes away, and I get 1/25. I still have room, that's why I keep erasing them. And then 3 times -2 is -6. So we don't want a negative exponent, so we bring it down to the denominator as a positive. So I get 1 over 25x to the 6th. take like 6 minutes and try the remaining couple.
And then we'll cover them.
All right, so looking over them, in number 3, you had x. Now I can make this a little bigger, fit to width. You had x to the 8th over 9. In number 4, you had 6x to the 5th. Because again, remember that 1/2 distributes both to the 36. And then it's 10 times a half, which is 5. In number 5, same idea. It becomes that 27 to the 2/3 as well as x cubed to the negative 2/3. They auto drop both to the denominator, saving that step with the negative, and then simplifying. 6 was 8 over x to the 4/3. 7 is 1 over x minus 2x to the 3/2 plus x squared, because when you take that negative exponent to the second and drop it to the denominator, that now makes it a binomial squared, which means you have to FOIL. So at number 7, you had to FOIL. That's how they get that middle term. So I think a lot of times you see it and you're like, oh, 1/2 times 2 is x. And then you get x squared. So you end up with like the first term and the last term, but we lose the middle term. Similarly, in number 8, a power to a power multiplies. So 2 times 1/2 becomes 1. Both go away and you get 1 over 2x minus 3. And then 9 was like a doozy. It took me like many steps just to like multiply the first 2 together, distribute the second one into the first 2, and then clean up all my exponents, multiplying them, adding them, etc. So you should end up with 1 over 2x to the 1/6 plus x to the 1/2 plus 1 over 3x to the 1/3. You can't simplify anything in that second part of the problem because you have a single term in the denominator and 2 terms in the numerator. The only way to simplify it would be to take the denominator under both, which you don't have to do. And then in 10, we had negative 1 over 6x to the 5/3. And in 11, the square root or x squared minus 16 to the 1/2. And then in 12, xy over y plus x. That one cannot be broken apart because you have addition in the denominator. So anytime you have an operation other than multiplication in the denominator, you cannot break it apart. It's like an algebra jail. So that kind of wraps up exponents and fractional exponents. Now we flow in to group and decay. So if the a value is a number other than 1, then we call that an exponential function. The domain of an exponential function is all reals. The domain is all reals. The range is 0 to infinity. The reason for that is because if you think about anything plugged in to that, you cannot get a negative. If a is positive, no matter what exponent I plug in, it will never be negative. If I plug in a fractional exponent, it just gets tiny. If I plug in a negative exponent, it just becomes a fraction. It doesn't become negative. And a to the 0 is always 1. So the 0 plugged in is never 0, so it's 1. So that's why the range is 0 to infinity. Compound interest investments and population growths are examples of exponential growth functions. Again, because a population can never be negative. We'd all be dead. Or extinct, I guess. That's a nicer word. So I don't teach bio. All right, in a graph for exponential growth, our a value in the equation, so that a is the number being raised to the power, must always be greater than 1 to represent growth. So the a value must always be greater than 1 to represent growth. Growth would start low and go high, again, never crossing the x-axis. Again, you can see here, at 0, it's at 1. Similarly, decay will have an a value that is a fraction. So you can see that in this example. I know it looks like it's a negative exponent, but taking into account our rules for negative exponents, that's really like 1/2 or 1/2x, but that could also be written as 1/2x, thus seeing the fractional power. So the constant k is, this isn't on there, I think it's just kind of like a little bit of into half-life. That constant k represents the initial amount. So if a population starts with 100 people and the population is doubling every year, the equation would look like y equals 100 times 2x, because the 100 represents your starting amount. So if you think back to when you did like interest formulas, they were always like the amount you deposited and then parentheses around 1 plus the rate over the number of compounds. Well, if you think about 1 plus the rate, that number is going to be greater than 1 because your account is growing. So let's look at an example. We have f of x minus 3. So when I see this 4, I immediately think growth. So starts low, goes high. The -3 tells me my graph is shifted down 3 units. So that -3 changes the range. It's going to move it so that my range is below 0. So now my range is 3 to infinity, or rather, sorry, -3 to infinity. So my range is -3 to infinity. Domain is still reals, and it said use your graphing calculator to find the zeros. So what you do is plug this into y equals on your graphing calculator. To find the zeros, you're going to use that second trace feature. And zeros are option 2.
Yeah.
Yeah, I don't have a calculator in front of me. I was like, 1 is exact. I'm like 2 zeros. The next one's like min or max. Actually, I think there's something in the middle.
Oh, my calculator just says invalid div every time I try to use y equals.
Hit y equals 1 more time. See if your plot 1 is darkened. Like,
Yeah, it is.
go ahead and arrow up and hit enter, and it will turn off your plots. Yep. Yeah, anytime you get like an error dim, it just means your plots are on.
Okay.
I wish it just said that.
Yeah.
You're not alone. Like, it happened to like 4 other kids in my class the other day, and I was like, ah. So hopefully once you do the second trace, have that plugged in, you get the same zero I got up on this board with my screenshot. I'm hoping to, like, since I bought my son a calculator, it has like the free software for the computer for a year, but I need to have Mr. Torjalis install it. So I'm hoping I'll have like an on-screen calculator this year.
Good, good, good.
Yeah, so today's kind of like a calculator day because a lot of these problems are going to be decimals. They're messy. They're like not pretty numbers. So growth and decay and exponents with crazy decimals tend to happen to be calculator problems. Exponential functions model real life phenomena. So when we have explosions or bombs, they leave off radioactive substances. So scientists calculate how long until an area is safe to return to. So a big area is Chernobyl. It's still technically unsafe. People try to sneak into it, and then they end up getting like cancers because they're exposing themselves to these harmful chemicals. So half-life is a way of calculating when half of a substance has been removed. Half-life is a really commonly used formula in chem. So we actually calculate a lot of half-life in calc, where we talk about, okay, at half-life, it no longer gives off radioactive chemicals, thus making it a safe location. The half-life formula in general is the natural log of 2 divided by k. So it's the natural log of 2 divided by k. K is that constant that represents its length of time. So over here, you can kind of see that this is a manipulation of y equals ka to the x. That y naught represents initial. So a little history on the word y naught. So before mathematics, everybody traveled by ship. So the reason we always call the initial y naught, and why you do it in physics as well, is because that was the nautical starting point for ships when they had to calculate like their paths with velocity on maps. So y naught actually came from the nautical starting point of ships on a map, and now we just kind of use it today. Some teachers will refer it to y to the 0 because 0 meaning initial time, but that's actually incorrect. But it is representing the initial value. E is a exponential marker for growth. It is that 2.83 number. It is a button on your calculator. So if we're talking about half-life and certain exponential problems like PERT, P-E to the RT, that's another compounding interest formula that uses E. So T is time, and then Y is the value at whatever time T is. So taking into half-life, it's half the initial at time T. And that's how you can calculate this. So let's try an example. It says, suppose the half-life of a certain radioactive substance is 20 days. So 20 days is my time. And that there are 5 grams present initially. So what that means is at time 0, y naught is equal to 5. So if the half-life is at day 20, then we know that half of y naught would be my y value at day 20, which means that this is 2.5. So I kind of have like 2 ordered pairs. I have 0, 5 and 20, 2.5. It asks, when will there be only 1 gram of the substance remaining? So I actually have to do 2 calculations. First is I need to solve for variable k. So I'm going to use the idea of the 1/2 y naught equals y naught e to the k of t. Because I know this is 2.5, 5e. I'm looking for t, or I'm looking for k when t is 20. K is a constant. Once I find K, that K value holds true for all the problem points. So, divide by 5. That isolates my exponential. So if my exponential is isolated, to get rid of an e, we use our inverse property of e, which is ln. So I'm going to ln both sides. What that does is cancel the ln and the e, and technically 2.5 divided by 5 could be reduced, and I'm going to have to use a calculator anyways to get my final value. So what you would do is say, okay, well now this is equal to k times 20. Solving for k means dividing both sides by 20. So k is approximately whatever the natural log of 2.5 divided by 20 is. Or 2.5 divided by 5 divided by 20. Yeah. So now the question is, when will there be 1 gram of substance? So same concepts, but now T is in question when Y is 1. But I now know K. K is approximately negative 0.0346. So what we're going to do is say, okay, 1 equals 5e. This time I'm looking for t, so I'm going to plug in k. And if you want k to be exact, we could say that k is really the natural log of 0.5 over 20 and not plug in a decimal. So you kind of have 2 choices. Personally, I hate kind of typing in decimals. I would probably type in ln 0.5 over 20 and just keep it on my calculator and work backwards to solve for t. So once again, we have to divide both sides by 5 to isolate the e, and ln both sides to get rid of the e, leaving me with ln 0.5 over 20 t. Flip it, so you get 20 ln 1/5 over ln 0.5 equals t. It's just a bunch of typing on a calculator. And you get 46.4385, which means on the 46th day, there will be 1 gram. So ironically, you turned off your stat plots. We're probably going to turn them back on. We have exponential regression. So exponential regression is a calculator feature given a set of data. You would plug it all in. So let's go ahead and put all that data in our calculator in L1 and L2. I'm going to grab my document camera, so in case you need to see some steps, we can. This program on the computer. All right, so what you're going to do is once you have all your data in there, you're going to hit Stat, go to Calculate, and this time we're going to go down to Exponential Regression. So it's EXP Reg, and then just go down to Calculate and hit Enter. So we should see that the A value is 56.46, the B value is 1.1 or 1.51. So again, a B value that is greater than 1 represents growth. The 56.46 represents the initial starting population. So now it says solve for x equals 12. So 1990 represented year 11. So year 12 would be 2000. So what you would do is, and I'm going to kind of cheat, like I'm going to go over here to y equals. I'm going to erase what's in my y equals. I'm going to hit vars. I'm going to go down to option 5, arrow over to equation, and hit 1 on reg EQ. And what it's going to do is take that last equation I calculated and put it in my y equals. So again, those steps are hit y equals, clear out what you have, hit vars, go down to 5 for statistics, arrow over to EQ, and hit 1 on reg EQ. And all it does is put that into y equals. And then if you want to know what x equals 12 is, you can go to graph. I'm going to go over to table because my table is always set to ask. So I can just type 12 in for x and get my y value. So you can set your table to ask by going to table set right here and changing independent to ask. And then that lets you type in any number you want on the table. As I said, like today's like a cool little calculator day. Okay, it says to calculate the percent error, but so percent error is simply actual minus findings. So the actual was given to you in that reading, and we found it to be 308.26, but the actual was 281.4. So what that means is that the population stopped growing as quickly as we originally calculated. So for percent error, you would just take your findings, which again, was 308 point something, my calculator. Here we go, 308.26. So I'm just going to hit enter, 308.261. So 308.261 minus 281.4. So it's actual minus experimental all over the actual. So you divide by 281.4. And if you times that by 100, our percent error is 9.545%. Again, my thing kind of froze again. So that is our regression. The last little bit is just that I said, like, we use the number e a lot. It's just this like irrational, naturally occurring number, kind of like pi. It's 2.71828, blah, 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 blah. It actually has a function for it, which is kind of cool. We never use it, but it exists. It's kind of like the z-chart in statistics. It has an equation, but you like never use it. You just use the z-chart. So we have e to the x and e to the negative x. They represent growth and decay, the same as a to the x and a to the negative x. Compound interest is PERT, where R is the investment, P is the initial, and T is our time. So then we have our equation for fruit flies. Let me tell you, fruit flies are awful. I hate them. I feel like I had fruit flies and they are so hard to get rid of. All because my kids left out a banana. An open banana. And like we left for a weekend and like came back and it was just like this infestation of fruity flies. And I was like, I had to buy like these little traps. It took weeks. I swear, it took weeks. They just kept birthing more babies. We know our equation. So yes, you can find the initial, but you should be able to remember that the initial is always the number in front. So initial is 20. Yes, you could plug in 0. Remembering that anything to the 0 power is 1 though, which is kind of why I show that, you still get 20. Because e to the 0 or anything to 0 power is 1. After 72 hours, you just plug 72 in and type this on your calculator. So you take 20e.003 to the 72, and you get 173 flies. So 3 days later, that's what I came home to, 173 fruit flies. I kid you not. There were probably 173 little fruit flies. And no kid wanted to claim that they left the banana out. I don't eat bananas, so I know it wasn't me. And then I think you guys can see a calculator graph. All right, so I wasn't sure of what homework I gave last year, but I went back on my Teams page. Hey, where'd it go? And I got their homework off there, and I thought I pasted it on here, and now it's like MIA, so let's just go back to last year's Teams. And I'm just hoping that whatever I assigned them last year is valid and accurate. So it's on page 26. It's this one. There you go. 1 to 4, 13 to 18, and 21 to 22. Super. Oh, look, I definitely copied you. Let's repaste you into my Promethean slide. Control V. Whoa. I pasted huge.